Welcome back to The Explainer. So, today we're tackling a topic that, let's be honest, sounds completely intimidating, but is actually beautifully logical once you peel it back. We're talking about support vector machines, SVMs. If you ever found yourself wondering how a computer draws that mathematically perfect line in the sand to separate really complex data, well, you're in exactly the right place. We're going to move way past the buzzwords today and actually look at the math under the hood. Let's get into it.
Here's our roadmap for The Explainer. First, a quick introduction to SVMs. Then, finding the optimal hyperplane. Moving into vector math and distances, functional versus geometric margins, and we'll wrap up with the optimization problem.
All right, Section 1. Introduction to SVMs and the basic mechanics.
At its absolute most basic level, a support vector machine is just a supervised learning pipeline. It simply takes labeled data as an input, data where we already know the answers, and processes it through the SVM algorithm to generate learning functions. And then it uses those functions to classify new, unknown test data. Simple enough, right?
But why do we actually care about this specific algorithm? Well, because it is insanely powerful. An SVM acts as both a linear and a nonlinear classifier, and it can even perform regression. What's really cool is its decision boundaries require just a small set of critical data points, the support vectors, which means it learns incredibly efficiently. Plus, it works seamlessly with higher dimensional data. That makes it literally the perfect tool for complex, real-world applications like facial recognition or, say, pedestrian tracking.
Moving on to Section 2, finding the optimal hyperplane, or basically, finding the best line.
Okay, imagine a scatter plot with two distinct groups of data points, right? Let's say circles and crosses. A hyperplane is simply the line, or if we're in higher dimensions, a flat plane that divides our input space. But here's the catch. If we want to separate the circles from the crosses, there are infinite ways to draw a separating line. I mean, you could tilt it a little to the left, maybe a little to the right, or shift the whole thing up. So that brings us to a massive question. Out of the infinite possibilities of lines we could draw to separate our data, which line is the actual mathematically provable best? Well, the optimal line isn't just any random line. It's the one that leaves the absolute maximum space, the maximum margin between itself and the closest data points from either class. Think of the solid center line as the middle of a highway and the dotted boundary lines as the curbs. We obviously want the widest possible highway. And those data points sitting exactly on those dotted curbs, they are literally propping up the boundaries. That is exactly why they're called our support vectors.
All right, Section 3, vector math and distances. Let's calculate that margin.
Let's look at how this builds mathematically. And don't worry, we don't need to jump straight into crazy calculus here. Let's just start with a standard 2D line equation, the one we all learned in school, y equals ax plus b. To make this actually work for multiple dimensions in an SVM, we just convert it into a formal vector notation, w dot x plus b equals 0. In this equation, w is our weight vector that tells us the direction of our hyperplane, x is our input data point, and b is the bias that shifts the plane around. To physically ground this math in reality, it's absolutely crucial to remember that in SVMs, data points aren't just floating dots. They are treated as vectors. Any point, like say the coordinate 4, 3, is defined as a directed vector starting right from the 0, 0 origin and pointing outwards to that exact spot.
So the real trick is figuring out the distance from that directed data vector to our dividing line. And for that, we use a very specific formula. Let's actually read it out. R equals h of x divided by the norm of w. Here, r represents the directed distance from our data point x to the separating hyperplane. And that norm of w, the w with the double bars around it, that's just a mathematical way of stating the vector's magnitude or its actual length. But remember, an SVM at the end of the day is a binary classifier. It absolutely needs to know which side of the line a point falls on. We handle this by introducing y, the target label. Y will simply be a +1 for one class and a -1 for the other. By multiplying our directed distance by these target labels, the classifier mathematically understands if a point is positively or negatively classified on the plane. Basically, if the sign matches, boom, it's correctly classified. Okay, Section 4, functional versus geometric margins, time to measure true distance. Let's really contrast these two ideas, because it's a common stumbling block. The functional margin essentially acts as a correctness indicator. It just tells us if a data point is classified correctly, like is it safely on its designated side of the line. But, and this is a big but,
It does not tell us the true physical distance. If you just scale the weights up, the functional margin grows, even though the line hasn't moved an inch. So to get the actual physical distance between the line and the point, we need the geometric margin. The geometric margin is a scaled, normalized version of the functional margin. That is what gives us the true, ungameable distance in space.
And there's a really fascinating relationship here. A smaller norm of W actually leads to a wider margin. It's an inverse relationship, which is a surprisingly neat mathematical trick. Because our distance formula divides by the weight vector norm, shrinking that weight vector physically stretches the margin wider. So minimizing the weight vector literally creates a better, cleaner separation between our data classes.
Tying it all together, we can just set our functional margin to equal 1 for our support vectors. This simplifies our ultimate geometric margin equation, let's call it m, to simply equal 1 divided by the norm of W. So mathematically speaking, our visual goal of making the widest possible street, maximizing the margin m, is exactly the same thing as maximizing this specific fraction, 1 over the norm of W.
Which brings us to Section 5, the optimization problem, and how we compute this at scale.
Look, if we only have, say, 20 data points, we can literally eyeball the graph, spot the support vectors, and draw the line ourselves. Visualizing it is super easy for small data. But this visual approach entirely falls apart for massive, high-dimensional real-world data sets. Imagine trying to process pixels in millions of images for facial recognition. You can't just eyeball 10,000 dimensions. So we absolutely must abandon the drawing board and reformulate this whole concept as a strict algorithmic optimization problem, something a computer can just solve blindly.
We start by stating the problem in its primal state. Remember how maximizing the margin means minimizing the weight vector? Well, here it is formally. We want to minimize 1/2 of the weight vector norm squared. But obviously, we can't just shrink it down to 0. It's a balancing act. We have to minimize it subject to a very strict constraint. Every single data point must be classified correctly, with a functional margin of at least 1.
Now, handling those constraints directly, it's pretty mathematically clunky. So, using calculus, we transform the primal problem into a dual Lagrangian problem. By using Lagrange multipliers, that little alpha symbol in the equation, we actually incorporate the constraints directly into the function itself, and this specific formulation is a total game changer. It is exactly what allows a computer algorithm to systematically and efficiently solve for the optimal line, even when we're dealing with millions of data points.
And honestly, that is the true magic of support vector machines. We started by simply drawing a wide street between dots on a graph, and logically followed the thread until we were utilizing advanced Lagrangian calculus to power real-world machine learning. So I'll leave you with this final thought. The next time your phone instantly recognizes your face, take a second to consider the math happening under the glass. How might transforming simple visual dots into a mathematical optimization problem change the way you look at everyday data classification? Thanks so much for joining me for this explainer. Stay focused and keep exploring the incredible math behind the world around us.